This video covers Section 5 of your Unit 7 Similarity flipbook. Section 5, bottom flap, bottom right-hand corner. The title of this video is Indirect Measurement. The essential question, class, is how do I use the properties of similar triangles to measure objects indirectly? Now, we talked about this in the beginning of the unit. I told you that we can use the properties of similarity to measure the height of mountains, redwood trees, flagpoles, all sorts of things, buildings. And this is one of the general ways that we do it. There's more than one way, but this is a common way to do it. Now, the question here is, how tall is the flagpole? And look at this diagram, class. You can see a number of things. One, there's some flagpoles standing out there somewhere, like the flagpole we have in front of class. When the sun is out, the sun will create a shadow of that flagpole. So if you can't see the picture of the sun on your on your flipbook, draw a picture of the sun and an arrow pointing to the top of the flagpole. Just say, class, the sun is in this position. It's going to cast a shadow on the ground. The bottom of this diagram represents the length of the shadow created by the flagpole. Now, here's what you can do to use similar triangles to figure out the height of that flagpole. If you stand in the shadow of the flagpole, and you're going to move back and forth until your top of your head is exactly lined up in the same place where the top of the flagpole shadow lands. So you stand in this position, and you're going to line your shadow up with the shadow of the flagpole. So now, I'm going to show you how cool this is and how we can use this to figure out the height of the flagpole. Okay? Now, if you draw a triangle using the flagpole as one side, the rays of the sun as another one, the bottom of the triangle is the shadow made by the flagpole, and then this line right here, which you can see, class, is parallel to the flagpole because you're going to stand straight up and down. You become the side of one of the triangles as well. And take a look, class. There's actually two triangles here. There's a big one, that's the outside, and a smaller one that's on the inside. If we can prove these two triangles, the big one and the small one, are similar, we can use the properties of similarity to estimate the height of the flagpole. So here's what we're going to write in our text right here. Angle ABC is congruent to angle angle DEC. Now, I forgot, class. I better label some vertices here. Let's label the top of the flagpole A. Let's label the bottom of the flagpole B. Let's label where the shadow of my head and the top of the flagpole hit the ground is C. We'll label the top of my head as D. And we'll label where my feet are as E. Okay, so if angle A, so we know that angle ABC is congruent to angle DEC. Class, those are right angles. The flagpole is built straight up and down, and I'm standing straight up and down, so we know those two angles are congruent. You want to put a little notation here. They're right angles, and I just use right angles. All right? Now, we also can know that angle ACB is congruent to angle angle DCB. Let's take a look at why that is. ACB is this angle right here. DC, sorry, that should be DCE, because that's our smaller triangle. DCE is the exact same angle. So those have to be congruent. If you remember, class, on this property right here, we called it the reflexive property. That means an angle is always congruent to itself. Reflexive. Get that right. Okay, reflexive property. Now, we've got two triangles where we have two angles that we know are congruent to each other. And we know what that means, class. So, based on that, triangle ACB Actually, you know what? Let's go A, B, C is congruent to triangle. Okay, A corresponds to D, so that must be letter D. B corresponds to E, that's the right angle, and C corresponds to C. That's a shared vertex of both of those. So we know these two triangles are similar, and they're similar by the AA similarity theorem. So now, based on this setup, we know we've got two similar triangles. Let's use it to find the height of the flagpole. And one thing we want to note now, class, what do we know about similar triangles? If triangle ABC is similar, you know what, class? I just realized I wrote ABC is congruent to DEC. That's getting us back to our integrated math 1 days. These are similar. If triangle ABC is similar to triangle DEC, then corresponding, remember we know corresponding sides are proportional. We can use proportions to find the length or the height of the flagpole. They are proportional. So let's set up our proportions. Make sure we match up correct sides here. So let's do that. So we've got, let's take a look, BC. Well, we're going to figure out what sides we know first, class. I labeled some things here. Let's say that EC was 8 feet. My shadow was 8 feet long. Let's say I'm 6 feet tall. And we also measured the distance from the flagpole to the top of the flagpole shadow, and that was 24 feet. So take a look. Let's write our proportionality statement and then use that to solve the flagpole. So here's our proportionality statement based on our similarity statement. We know that AB over DE is equal to, there's our first two positions. Here's our second two, BC over EC. And that's proportional to third and first positions, CA over CD. So we know these proportions are true. Let's find the ones we're going to use. Well, we're trying to figure out what AB is. So we want to use this proportion because I want to know what AB is. Let's find the proportion now that we know both measurements. BC, yep, we know that. EC, yep, we know that. This is our other proportion we're going to use. Now, let's take a look at the third one just in case we could use that as well. CA, oh, we don't know the length of CA, so that one's out. We can't use that one. So we're going to use these two ratios to find the height of our flagpole. All right, so let's find out. What is AB? That's our unknown. That's X. What's DE? That's my height, which is 6 feet. What is BC? The distance from the flagpole to the top of its shadow. That's 24 feet. And the distance from E to C, that's my shadow, and that's 8 feet. Notice, class, I'm not writing feet anywhere because everything is the same measurement, so we don't have to write the unit of measure. Okay, let's go ahead and cross product on this. This is going to be 8x is equal to 6 times 24. So 8x is equal to, let's see, 6 times 24 is 144. Divide both sides by 8, and x equals 18. So we just found our missing side here, which was x before, is now 18 feet. So using similar triangles, we just found out the flagpole is 18 feet tall. And now you can see, class, how we can use similarity and similar triangles to find heights of all sorts of things. Trees, buildings, even mountains can be found by using similar triangles. All right, one more thing in the end of this video. This is not the only way that we can use similar triangles to measure the height of things. We're going to actually use this next method in class in a couple days. So let's take a look at my text if you write this down. You can also estimate the height of an object by placing a mirror on the ground and creating similar triangles. So take a look at what's happening here. Here's our flagpole again. Okay? And then we have me standing here a little distance away from the flagpole, and we're going to put a mirror right here on the ground. Alright, and I'm going to look, my eyeballs right here, I'm going to look with my eyes down into the mirror, and then I'm going to be able to see the reflection of the flagpole, and based on where that mirror is, I'm going to back up and get closer. I'm going to move myself around until when I look in that mirror, I exactly see the top of that flagpole. And when I do that, then I'm going to measure the distance from the mirror to my feet and the distance from the mirror to the flagpole. And if I also measure the distance from the ground to my eyes, you can use similar triangles to figure out the height of the flagpole. Now here's the confusing part for you. We know that when I stand up on the ground, I can stand straight up and make a right angle. And I know that the flagpole is straight up and down from the ground too, and that's a right angle. But in order to prove these two triangles are similar, I'm going to need another angle that is congruent. This is something that we learn in physics. It's also something that you learn if you've ever played pool. If you've ever played pool on a pool table, you learn that when you strike a ball and it bounces off the cushion, when it reflects off the cushion or bounces off the cushion, the angle that it was traveling when it hit the cushion is exactly the angle it's going to be traveling as it leaves the cushion. It's the same with light waves. If I look in the mirror, the angle of my vision as I look straight into that mirror, as it reflects off the mirror and goes to the flagpole, the angle of entry of those light particles is the exact same as the angle of exit. So you can see with this particular diagram, we actually have two triangles that are similar because we have two corresponding angles that are congruent. These triangles are basically reflected and then dilated. So based on this, and I'm going to put a little note here saying we're looking down in this mirror, the light ray is going to come up and look at the top of the flagpole. We'll use this in class to actually figure out the height of a tall object on campus. So these are basically two methods, not the only methods, but two methods that we can use to use the properties of similar triangles to find the height of objects that might be very difficult to measure with the tape measure.